From Fire to Sound, The Astonishing Physics of Thermoacoustics. Introduction: The engine that runs on sound. Imagine an engine that needs no gasoline, no electricity, and has no complex moving parts. Instead, it is powered by sound itself. Picture a device that can capture waste heat from a factory or the intense energy of the sun and transform it into powerful sound waves capable of cooling entire buildings. This might sound like science fiction, but it's a real and revolutionary field of physics known as thermoacoustics, a technology once confined to laboratories that is now poised to change our world. It is the science of turning heat into sound, and sound into powerful, useful work. 1. The simple secret of sound. Understanding resonance. To grasp how heat can generate such power, we first need to revisit a fundamental principle of sound: resonance. You have likely experienced this phenomenon yourself. When you blow carefully over the top of a test tube or a glass bottle, you produce a clear, distinct musical note. This sound isn't magic. It's a simple cycle of physics in action. Your breath causes the air inside the tube to compress and then expand. When the timing of this compression-expansion cycle perfectly matches the tube's natural frequency, the vibrations amplify each other, creating a loud, stable tone. This is resonance. From this simple experiment, we can draw two key insights. Tube length. The length of the tube is what determines the pitch, frequency of the sound. A short tube produces a high-pitched note, while a longer one produces a lower-pitched note. Wavelength rule. For resonance to occur, a simple physics rule must be met. The tube's length must be equal to a quarter of the sound's wavelength. But if a simple puff of air can create a resonant sound, what happens when we introduce intense heat into the equation? 2. Making a tube. Sing how heat creates sound. The phenomenon of heat creating sound is not new. 19th century glassblowers first noticed that hot glass tubes would sometimes spontaneously begin to sing with a powerful tone. The physicist Sondhaus later proved this was linked to the temperature difference. A simple yet powerful experiment demonstrates this core principle of thermoacoustics. The setup consists of a test tube with a small piece of steel wool, known as the stack, placed partway inside. One end of the tube is then heated with a flame while the other end is kept cool. At first, nothing happens, but then an explosion of sound erupts from the tube, a loud, booming, continuous tone that can reach an astonishing 88 decibels. This incredible effect is driven by a rapid, self-sustaining cycle. 1. Air near the hot end of the tube expands rapidly, causing it to rush through the stack toward the cool end. 2. Upon reaching the cool end, this parcel of air rapidly contracts. 3. This contraction pulls the air back toward the hot end, where it heats up again and repeats the cycle. When the frequency of this heating and cooling cycle perfectly matches the tube's natural resonant frequency, the silent, invisible heat transforms into a powerful, continuous sound wave. The tube is literally singing with fire. However, this powerful effect doesn't happen by accident. It relies on a brilliant principle of timing discovered over a century ago. 3. The Golden Rule. Lord Rayleigh's principle of timing. The secret sauce for turning heat into powerful sound was articulated in the 19th century by the brilliant scientist Lord Rayleigh. He discovered that to amplify a sound wave using heat, timing is everything. He formulated a golden rule that remains the foundation of thermoacoustics today. To amplify a sound wave, you must give it heat at the moment of maximum compression and take it away at the moment of maximum expansion. In simple terms, this means you must add your energy at precisely the right moment to strengthen the wave. By adding heat just as the air molecules are already squeezed together, maximum compression, you give them a powerful extra push, dramatically increasing the wave's amplitude and turning a small vibration into a powerful sound. It's like pushing a child on a swing. If you push at the exact right moment in their arc, they go higher and higher. If you get the timing wrong, you hinder their motion. With this principle unlocked, scientists could design machines that don't just make noise, but do real work. 4. Building the machine, the thermoacoustic engine. This is the moment where a laboratory curiosity becomes a revolutionary machine. The loud, resonant sound wave created in the tube is, at its core, a series of intense, high-pressure pulses. So, how can this be harnessed? Imagine we seal one end of our singing tube and place a piston there. The powerful trapped sound waves now have nowhere to go. Instead, these high-pressure pulses push and pull on the piston, forcing it into a fast, regular back-and-forth motion. If this piston is connected to a wheel, its linear motion can be converted into rotational motion. Congratulations! You have just created a thermoacoustic engine, a device that transforms heat into sound and sound into mechanical work. This type of engine has three primary benefits: simplicity and longevity. With no internal combustion, no explosions, and no complex valves, they have very few moving parts. This means they require little to no maintenance or lubrication and can live for long periods. Clean energy. When powered by a clean source like the sun or industrial waste heat, they turn otherwise wasted energy into productive work with zero harmful emissions. Quiet operation. Even though they are powered by sound, the engine can be designed to keep the resonant wave trapped inside, making the machine itself remarkably quiet. So, if heat can be transformed into powerful sound, could the reverse be true? Can we use sound to make things cold? Conclusion: a future powered by sound. The journey of thermoacoustics reveals physics in its most beautiful form. By harnessing the simple expansion and contraction of air, combined with the power of resonance and the genius of precise timing, we can transform simple heat into a powerful sound wave. That sound can then be converted into useful mechanical work or, incredibly, used for cooling. The process is reversible. A powerful sound wave sent through a tube can create an intense temperature difference, a phenomenon known as thermoacoustic refrigeration. These devices have no moving parts and no harmful gases to leak, making them ideal for mission-critical applications in spacecraft or remote places where reliability is paramount. It's a revolution happening now. The Dutch company Sound Energy already deploys this technology, using waste heat from factories to cool industrial buildings without using a single drop of Freon. Thermoacoustics proves that the fundamental laws of physics hold astonishing potential, waiting for us to listen and innovate our way toward a cleaner energy future.
Thank you for watching this video.